Hi, and welcome to another video tutorial on microcontrollers for Engineering 290 at San Francisco State University. Today we're going to look at serial communication, a widely used method for transferring data in between logic devices. To give an overview of the tutorial, we'll look at the differences between parallel communication and serial communication. We'll also look at some serial peripherals commonly found in microcontrollers. And in particular, we're going to focus this discussion on one peripheral called the USART. The USART has some control and status registers that govern its operation, and we'll talk about adjusting its speed at how fast you transmit data. And finally, we'll finish up looking at some examples of how to set up for a transmission, an example routine on how to transmit data, and we'll look at using some standard library functions from the standard I/O library to print formatted text. So in parallel communication, we can see the transmitter on the right and the receiver on the left, and an entire byte of data is transmitted all at once. So the number of wires needed to transmit a byte of, let's say, n bits is, well, it's n wires. And the nice thing about this is that all of the bits, the entire amount of data, is transmitted simultaneously. And as a result, the transmission can be done feasibly in one clock cycle. Contrast that with a serial communication protocol, in which we have the transmitter on the right, the receiver on the left, and data is sent down only one wire, no matter how many bits there are. And each bit goes down the pipeline, one after the other, down the wire. In this case, you have the most significant bit leaving down the wire first and arriving at the receiving side first, so that we sort of have the data output on the transmitter side connected to the data input, DI, on the receiving side. And since the bits travel one at a time down the wire, and each bit is transmitted every clock cycle, the transmission takes at least n clock cycles. So you can see that there are two very big differences with regard to transmission speed between parallel and serial communication. Now, clearly, one of the pros of parallel communication is that it's really fast. Unfortunately, that comes at an expense, is that it requires a lot more wires for transmission, at least as many as there are bits. And you may need to also provide a clocking signal between the devices so that they know when to read the data. Now, the obvious pro or plus for serial communication is that only one wire is required for transmission. The nice thing about that is it reduces the number of I/O pins needed for a particular application. And it's also easily adapted to schemes that really require only one wire or one medium for transmitting data, such as infrared or wireless. Of course, that comes at a cost. It's inherently slower than parallel transmission, but it's relatively easy to really ramp up the transmission speed so that you can have still robust and quick communication. So some of the devices that use serial communication are, well, almost all the consumer electronics you use in your daily routine. Wi-Fi for a laptop to a wireless station is serial communication. All your Bluetooth devices also send data one bit at a time over a wireless or radio link. Depending on the protocol, whether it's Wi-Fi or Bluetooth, they still transmit data one bit at a time, and thus are serial. A few of the peripherals that you commonly find in microcontrollers are listed here. One is the serial peripheral interface, or the SPI. This is often used in multiprocessor systems. Incidentally, it's the same port that is used to download the hex file that you program in let's say, an Atmel Studio for Atmel microcontrollers. When you compile that machine code and download a hex file through a programmer to your microcontroller, the data is transferred over to the SPI interface. There's also the two-wire interface, or the inter-IC interface, or I2C. It's worth noting that this platform it forms the base protocol for the CAN bus system found in all modern automobiles. And the focus for our topic today is the universal synchronous asynchronous receiver transmitter, or the USART, widely used in a number of applications. So it's a two-wire communication scheme, and the pins that are associated with it, commonly found on a device that supports USART communication, are the TX pin for transmitting, the RX pin for receiving, and the clock pin for transmitting a clock signal if used. If you've heard of RS-232 protocol, that's a widely used device, an earlier version of serial before USB was available, for example. It's also still largely used in avionics. And the USART employs the RS-232 protocol for some very convenient reasons. Now, the other thing about the USART is that it, as any serial device does, it runs at a certain speed, termed the baud rate. And this is a measure of the bits per second, how fast bits are transmitted down the wire, down the media, per second. And this is chosen by the clock frequency. So those are things we're going to look at. Now, you can run the USART in either synchronously or asynchronously. Let's focus for a moment on the left diagram on synchronous transmission. If you have two devices, device 1 and device 2, usually their TX and RX lines are connected reciprocally to one another. So the TX line from device 1 connects to the RX line for device 2, and vice versa from device 2 to device 1. They both also share a common clock signal, that they're clocked to the same rate. We also see that on the asynchronous side, that device 1 and device 2 are still interconnected through their TX and RX lines. And in this case, there is no clock signal. So the clock doesn't need to be transmitted. Each device then uses its own internal clock. Each device has clock generating circuitry, and those clock frequencies must be set to the same frequency. So in asynchronous mode, which is one of the mode we're going to explore today in this tutorial, and you'll do in the lab, in the following lab, is that both devices use their own clock signal. Each transmission then, each data message set of bits is framed between a start and a stop bit. And that helps the receiving end determine when the message begins and which bits are data. There's also something called a parity bit that can be included into the message packet, which is used for error checking. Since there are these various bit schemes, both the transmitter and the receiver have to be configured or set up for the same transmission and reception specs. In other words, the same baud rate, the same number of data bits, which is configurable, the same number of stop bits, which is also configurable, and whether there's a bit for parity check or not. The way this scheme looks, if we're to look at an example waveform, an example message transmitted, we can examine the data bits and the framing. So if you start, what we're looking at over here is an example waveform as time goes on. And all the way on the left of the diagram, we can see that before transmission begins, the TX pin of the USART peripheral idles high. And on the next, we're looking at each on each vertical or horizontal segment here, marked by the dashed lines. We're looking at the next clock edges. So on one of the clocks here, the TX line falls low, and the falling edge of the start bit begins the timing sequence in the receiving device. The next bits to follow are the data bits. And what the receiver does is it waits 1.5 bit times before sampling the first data bit, so that it's sampling effectively in the middle of the data bit. So it samples in between, right smack in the middle, in between two clock edges, so that you're sampling in the middle of that clock period, so that any transient information when the bit went either high or low is settled, and you get a reliable reading of a measurement of whether the bit was high or low. Each successive bit is then, of course, sampled in the middle of its sequence. And finally, all the way at the right side of the page, the rising edge of the stop bit signals to the receiver that the whole data byte has been received, and the receiver then does whatever it does with that data byte once it's been parsed in. An example where asynchronous transmission is really useful or sometimes required is in radio transmission. We have an example of an RC controller sending signals to an RC plane. And there's clearly no wire connected between these, so it's difficult to implement a separate channel for a clock signal. Thus, this is one scheme that really requires asynchronous transmission. Now let's look at the USART subsystem in the Atmega16. This diagram I've put together has a zoomed in area of one side of the chip where we're looking at just the USART system itself. There's a large data bus shown on the left, which traffics data bytes command messages to registers to and from the CPU. In the upper left of the USART, we see the control and status registers A, B, and C. They're named the USART control status registers, or the UCSR. These registers configure how the USART operates, and also they have some certain flag bits in there that give status messages about how what the USART's current status is. We also have the UDR, which is the data register. And this is where data is sent to transmit and read from to receive. And because the data register itself is an 8-bit register, to send out a single bit at a time, you need a small register-to-pin interface, which is shown just to the right of that. And that essentially consists of a shift register with a single flip-flop connecting to each one of the pins. And finally, at the lower left, you see the baud rate register, the UBRR. Loading a particular value into that device tells the clock generation circuit, shown in green in the lower right, how fast to operate. So we have a method from the CPU to load a byte of data into the UBRR and tell the clock how fast to run. All right, so we're going to look at a few of these registers in detail in the next few slides. Just to recap, the data register is the UDR. It can be written to transmit a byte, or it can be read from to read a byte that's been received. We're going to focus a lot on the control registers, UCSR A, B, and C. Those, as I mentioned, govern the operation of the device. And finally, we'll take a look at the baud rate and specifying the clock signal and some limitations with defining the clock signal. So the USART control status register A, or UCSRA, contains a couple of bits that really have some useful status information. One of the most important ones we're going to use in this exercise and in the following lab is the UDRE flag, or the USART data register empty flag. This flag indicates if the UDR, the data register, is empty. So the flag is automatically set to 1 when it's empty. And that provides a really convenient way for a programmer to check to make sure that the data register is empty. That means that no transmission is going on or taking place. And it's safe to write a byte of data to the UDR without overwriting some other data. Another pin we'll look at, or another bit we'll look at, is the U2X. Setting this bit high enables something called double transmission mode, which we'll talk about the importance of that momentarily when we look at the clock generation circuit. But essentially, it lowers the percent error of the generated clock frequency, which we'll discuss more in a moment. Finally, just to look at a couple of other flags which are useful. We won't be using them in this tutorial, but bit 6 and bit 7, the TXC and RXC flags, those are flags that go high when a transmission is complete for TXC or a reception is complete for RXC. and they can be useful in certain applications. The next control status register, UCSRB, contains a really important bit. In fact, a few important bits to turn on to enable certain features of the USART. In today's tutorial, we're going to look solely at transmission. So bit 3 contains the flag TXEN, or enable the transmitter. Setting this bit to 1 turns on the USART transmitter circuit. This register also contains the RX enable line, which is bit 4. It contains, in bits 5 through 7, certain bits to enable interrupt functions, which we'll talk about in another video, which is an efficient way of using peripherals. And finally, the control status register C, UCSRC, is the device that selects whether the USART runs in synchronous mode or asynchronous mode. It also specifies the framing, which can choose the number of data bits, the number of stop bits, and whether or not you're going to use a bit for parity checking and error checking. To set whether the USART runs synchronously or asynchronously, that's specified with bit number 6 in this register, the UMSEL, or the USART mode select. If you set this to 0, the USART runs asynchronously, or in the so-called UART mode. UC SZ1 and SZ0 choose the number of data bits. Okay, and the number of data bits is set on this slide here. This is at table number 66 out of the data sheet, and you can see that in the 4th row down, we can set the number of data bits to be 8 bits. Setting UCSZ0 high and UCSZ1 high. 8 bits is a very common data bit size, since in that way you can send an entire byte of data in each message. I'd like to talk for a moment about the clock generator circuit. At the top of the diagram, the UBRR, the USART baud rate register, is a register that you can load a value into, and from that value it chooses a pre-scaling down counter. This essentially determines what percentage of the master clock signal that's running the entire chip. The clock is derived, the USART's clock is derived from the master clock, which it's titled FOSC, or the frequency of the oscillator. And so, since it's derived from that, there is it can only be certain multiples, or rather divisions of the master clock, and so that imposes a limit to which frequencies can be generated. You don't have, as a programmer, full access to generate any frequency you desire. It has to be a division of the master clock frequency. Now here's a table out of the data sheet, table 68, which lists the baud rate register numbers for configuring the USART to run at certain transmission speeds. So on the left you see the baud rates are listed in BPS as 2400, 4800, 9600, 14.4K, and so on. These are commonly used baud rates that many devices, they've sort of been standardized. Many devices have the ability to set their receiver or transmitters at their clocks at this rate. So in each of these 3 columns here, you're seeing what value you should write to the UBRR, depending on what your master clock frequency is. And we're seeing 3 cases here for 1 megahertz, 1.8432 megahertz, which we'll come to back to in a second, and 2 megahertz. So we can see that for the 1 megahertz signal, if I wanted to run the USART at, let's say, 9600 baud, we can see that I'd load, if I wasn't using double speed mode where U2X was 0, you could see that I'd load the value 6 into UBRR. And that says, in the next column, it says there's an error associated with that. It says it's minus 7%. Well, an error from what? Well, it's the error between which the actual clock frequency is going to be how far away it is from 9600 bits per second. So it's in fact 7% low of 9600 bits per second. And that's because with a 1 megahertz clock, by dividing from a 1 megahertz clock, the closest you can get to 9600 bits per second is 7% below it. Now, if you instead use double speed mode, you can in fact, where U2X is 1, you can load a value of 12 into the UBRR for a 9600 baud rate, and the percent error drops dramatically to only 0.2%. It's only 0.2% higher than your target 9600 bits per second. Let's briefly look to the second column, where the master clock frequency has been set to 1.8432 megahertz. That's a suspiciously particular crystal oscillation frequency. And you'll notice that for all the divisors, for any of the baud rates, the percent error is 0. Well, except for one all the way down at the bottom, which is because the divisor is getting so low at that point. That's the fastest you can run it at, is really at 57.6K. But that's the reason that this oscillation frequency has been chosen, is so that because it provides an even multiple for a specific baud rate. So if you've ever opened up a logic device, some piece of consumer electronics, and you see a CAN crystal in there, and the crystal reads some arbitrary particular frequency like 1.8432 megahertz, you now know that that's been chosen so that divisions of that work out to be an exact multiple, or an exact version or target of the, they target the frequency quite well. Okay. So if I wanted to, let's look at a quick transmission setup example. If I wanted to configure the transmitter, I wanted to enable the transmitter, I wanted to turn on double speed mode, I wanted to choose 8 data bits, 1 stop bit, run the thing asynchronously, and transmit at a 9600 baud. This example will go through the value you would load into each of these registers. So first, let's talk about enabling the transmitter. Remember, that's done by setting the TXEN bit high, which sits in UCSRB. So we write a 1 to TXEN. Now, if I want to use double speed mode, remember I write a 1 to the U2X. Okay. And now we want to look at the number of data bits and the stop bit and running it asynchronously. So what I do here is then, from the previous slides we looked at in UCSRC where that's chosen, if you look back at the table, to run it for 8 data bits and 1 stop bit, I set UCSZ1 and UCSZ0 high. And if you look through the datasheet, it also recommends setting bit number 7 of UCSRC high, the UR select mode. It says when writing the UCSRC to write this bit as 1. Now it actually has an initial value of 1, but to be safe, you can write it as 1. Now the syntax for accomplishing that I have written down here in the lower left corner, where we can see that for UCSRA, we're going to load the value hex 02, setting bit 1, the U2X line high, to enable double speed mode. You can also notice that for all the register writes, besides the baud rate register at the bottom, I've done them with an OR operator, so that I've ORed the register with itself and the hex value I want to turn on particular bits. And remember, you'll recall from the earlier tutorials that sets certain bits high without affecting any other bits, without overriding any other bits, which is a very useful method. And consequently, subsequently, the UCSRB and the UCSRC writes are shown there as well. Now I wanted to bring up an alternative method for writing this syntax, which is shown on the right. And this was covered in an earlier tutorial, but these register writes accomplish the same thing as what is listed on the left. You'll recall from the earlier tutorial that the avr/io.h header file, which contains the mappings for these register names like UCSRA to their address in the controller itself, they also contain names for the bit positions in each of those registers. So for example, if I wanted to take a 1 for UCSRA, I wanted to take a 1 and then left shift it twice to load it into U2X. Well, U2X has the hex value 0x02, so I'm left shifting it. Actually, it has the hex value 1, so I'm left shifting it by 1. Okay, and that's how the other ones go as well. You can look through that. Finally, by the way, the UBRRL, the low byte of the USART baud rate register, is loaded with a value of 12 to give a 9600 baud transmission speed. Now we can look at an example of writing a function to transmit a character. So the initialization that we just saw is done here in main, and you can see those same values written down there in the code. And I've written a function outside of main called UART put char, or the UART put character, which takes at its input a character called C. And all the USART put char or the UART put char function needs to do is to transmit a character. And that's done with the line down just above the return 1 line in the UART put char, where the data C is loaded to the UDR, and that transmits the data. But before we transmit the data, remember we want to make sure the USART is empty, or the UDR, the data register, is empty. And to do that, we can check the UDRE flag. So the while loop above loading the data to the register to the UDR accomplishes this. It checks to see while the UCSRA, while the UDRE bit is still 0, because we want to wait until it's a 1. While it's 0, we're going to sit there and hang out in the while loop and just keep looping until that UDRE flag goes high, and then we know that we can transmit the data. All right, last, before we finish our tutorial, there are some standard functions in the standard I/O library that allow you to send more than just a single character or do some other things as well, which are useful to use. There are some functions called getChar and putChar, which get and put characters to the serial port. You can put an entire string of characters out the serial port with a function called putS, or as some people call it, puts. Printf is something we'll look at on the next slide, and you'll also look at in lab, which is a highly customizable function to print a formatted string to the serial port. And that string can contain both alpha and numeric text. Sprintf accomplishes the same thing, but it actually stores the formatted string to a character array for other uses in the program. So in using printf, a couple of identifiers or formatting commands are really useful to get familiar with, including any of these characters allows you to move the cursor around and also specify how the data should be printed. So a \n moves the printout cursor to a new line. A \r does a carriage return. The name is sort of carries over from back in the day with typewriters, where they in fact would have to return the carriage, which carried the stroke keys, the keystrokes, back to the front of the paper. This accomplishes the same thing. It moves the cursor back to the left side of the screen. And percent signs indicate used inside of this inside of the quotes, inside of the text strings, they indicate where a numeric number is going to show up. And the letter after that % specifies what kind of number it is. A D for a decimal or integer number, an F for a floating point number, and there are many others that you can look into. So an example of that would be shown here, where you can see we've included the standard I/O library, we've set up main, I've got a char variable called sensor reading that I've set equal to 135. And in the after the initialization is done, which contains the same code we use to initialize the transmitter, we're using the printf function to transmit a value or a string that says the current sensor value is, and you see a %d sign and a couple of \n and \r to clean up the terminal viewing, and we load a sensor reading. We load the, or I should say, the number we're placing there is the sensor reading, and that's placed where the %d sign is. So the value inside sensor reading is in fact placed in the %d in the placeholder in the string of where the %d sign shows up. So the serial terminal printout would show up as shown here, where if you were looking at that in a serial terminal, we would read that as the current sensor value is 135. Now, I should like to look at an example terminal program just for a moment to show you where that would look like. So here is in the middle of this screen. This is a program called term, which acts as a serial terminal to connect to other devices, and the displayed text would show up in the middle of the screen here. Now, if I'm running this asynchronously, I can set up the transmission and reception properties here. So I could choose a 9600 baud rate, I could choose 8 data bits and 1 stop bit, no handshaking, and then I would choose the correct COM port. And once I had done so, I could click connect, and I'd be ready to both transmit and receive data. And that received data would show up here. So anything I was printing from my microcontroller, let's say the serial terminal printout, this text would show up in the middle of that window. To summarize what we've talked about today, we looked at serial communication in general and how it differs from parallel communication. We talked about a few different types of serial communication that are supported in a microcontroller. And we focused most of the discussion on the USART. We looked at how to configure it for transmission. That largely had to do with setting the control and status registers. And we looked at an example transmission scheme where we made use of monitoring the status flags, for example, like the UDRE, and we saw how to transmit data just by writing to the UDR. And lastly, we also looked at using standard I/O library functions. That concludes our talk for today. You'll follow up with this more in the lab. See you then.